Hello! In this video, we are going to prove the following theorem. Let A and B be sets. If A and B are finite and disjoint, then the union of A and B is finite. Moreover, the number of elements in the union of A and B is equal to the number of elements in A plus the number of elements in B. Okay, now before we get into the proof, let's get some context. Now to start, we're going to say that given any two sets, A and B, we will write this to mean the same thing as saying there exists a bijection from A to B. Okay, now let's talk about some properties of bijections. One of the properties is, given any two sets A and B, if there exists a bijection from A to B, then there exists a bijection from B to A. Another property is, given any three sets A, B, and C, if there exists a bijection from A to B, and there exists a bijection from B to C, then there exists a bijection from A to C. There's also a property of bijections involving disjoint sets. And the property goes like this. Given any four sets, A, B, C, and D, if there's a bijection from A to B and a bijection from C to D, in addition, if it's also the case that A and C are disjoint and B and D are disjoint, then it turns out there is a bijection from the union of A and C to the union of B and D. And I'm going to call this third fact theorem star. Now, let's talk about what we mean by finite sets. For us, we're going to say that the natural numbers includes 0. And for each natural number n, we define the following set. We define the set In to be the set of all positive integers that are less than or equal to n, where the positive integers are just the natural numbers, not including 0. Okay, now, let's talk about what it means for a set to be finite. Now, we're going to say that given a set A is finite if there exists a natural number n such that we have a bijection from In to A. And it turns out that if we have a finite set A, well, yeah, by definition, there exists a natural number n such that there is a bijection from In to A. But it turns out that this natural number n is the only natural number such that we have a bijection from In to A. So it turns out for finite sets, there exists a natural number n that satisfies this condition, and that natural number is unique. Right? And we proved the uniqueness of this natural number in a previous video. So yeah. And so we'll denote this natural number n in the following way. Just like this, right? So really, we call n the number of elements in A. All right, so now we're ready to get into the proof. To start out our proof, let's give ourselves two sets A and B, where A and B are finite and disjoint. Now, based on what we have written here about finite sets, we know that every finite set is assigned to a unique natural number n, which we denote symbolically like this. So, since A is finite, we'll assign A to the natural number n, and we'll assign B to the natural number n. Right? And what this means is that n is the unique natural number such that we have a bijection from In to A. Similarly, m is the unique natural number such that we have a bijection from Im to B. Okay, now remember, our goal is to show that the union of A and B is finite. In particular, we want to show that the number of elements in the union of A and B is equal to n plus n. And by the definition of finite sets, what this means is we want to show that n plus m satisfies the fact that we have a bijection from In plus n to the union of A and B. So this is our goal. And to prove this, notice we're dealing with bijections and we have a union of disjoint sets. So maybe we can try applying theorem star. And to see how we can apply theorem star to obtain this, let's do a little bit of scratch work. Now, to start, we can think of the set In as follows. And we can think of the set Im as follows. And to bring In plus m into the picture, what we're going to do is we're going to take the elements of Im and add n to each of them. And if we do that, well, we're going to have n plus 1, n plus 2, and so on and so forth until n plus n. And so all these objects together make up In plus m. And these elements together make up In plus m set minus In. And we have a bijection from Im to In plus m set minus In. And that bijection is defined by taking each element of Im and adding n to it. So we can define a bijection from Im to In plus m set minus In by taking each element of Im and adding n to it. And then after we show this, well, what other bijections do we know? Well, we know that there is a bijection from In to A. We know there's a bijection from Im to B. And we will have just shown that there's a bijection from Im to In plus m set minus In. However, with this knowledge, we can then use fact 1 and 2 about bijections to obtain that there's a bijection from this set to B. And now we can use these 4 sets to apply theorem star. And to see how, if we take A, B, C, and D that we have here to be these 4 sets in order respectively, well, we see that these 2 sets are disjoint and these 2 sets are disjoint. By theorem star, it follows that there is a bijection from the union of these 2 sets to the union of A and B. Well, the union of these 2 sets is just In plus m. So we will have a bijection from In plus m to the union of A and B, which is what we want. So this is our plan. Now we're going to execute it. Let's recall our first step. Our first step is to show that there's a bijection from Im to In plus m set minus In. In our scratch work, we found that if we take each element of Im and add n to it, well, that creates a bijection, visually speaking. So let's define that function right now. We define a function f over domain Im by the formula that we have here, right? We take each element I in Im, add into it. That's the output value. Our claim is that f is a bijection from Im to In plus m set minus In. Well, first, we need to show that f is a function from Im to In plus m set minus In. And to do this, we're going to show that for all I in In, f of I is an element of In plus m set minus In. So this is what we're trying to prove. And since we're trying to prove a statement about all elements of Im, give me an arbitrary element of Im. I'll call it I. And our whole goal is to show that f of I is an element of In plus m set minus In. Now to start, since I is an element of Im, well, what is In? Well, Im is precisely this set where we replace n with m. So, I is a positive integer, and I is less than or equal to n. And And since I is a positive integer, we have that I is greater than 0. And we're trying to show that f of I is an element of this set. And f of I is equal to I plus n. So we should try to bring I plus n into the picture. Well, we can do that if we just take this inequality and add n on all parts of it. So if we add n to all parts, we're going to get that n is less than I plus n, which is less than or equal to n plus n. Now, since I is a positive integer and n is a natural number, surely I plus n is a positive integer. So since I plus n is a positive integer, and I plus n is less than or equal to n plus n, it follows by definition of I n plus n that I plus n is an element of I n plus n. Now, because I plus n is greater than n, this means it is not the case that I plus n is less than or equal to n. So, I plus n does not satisfy this condition, which means I plus n is not an element of In. So, I plus n is an element of In plus n, but not an element of In. So, I plus n is an element of this set. And we know that f of I is equal to I plus n. And putting this together, we gave ourselves an arbitrary element I in In. From there, we showed that f of I is an element of In plus n set minus In. And since I was an arbitrary element of In, this means for all I in In, this is true. So we have proven precisely this statement, which amounts to proving that f is a function from In to In plus n set minus In, which is what we wanted. So now that we've shown f is a function from In to In plus n set minus In, now we want to show f is a bijection from In to In plus n set minus In. And to do that, we're going to show that f is both injective and surjective. Let's start by showing that f is injective. And to show f is injective, what we're really trying to show here is, for every two elements, I1 and I2 in In, if f of I1 equals f of I2, then I1 is equal to I2. So let's give ourselves two arbitrary elements, I1 and I2, in In. And suppose that f of I1 is equal to f of I2. Our goal is to deduce that I1 is equal to I2. And to start, well, we know that f of I1 is equal to I1 plus n. F of I1 is equal to f of I2, and f of I2 is equal to I2 plus n. So I1 plus n is equal to I2 plus n. Subtracting n on both sides, we obtain that I1 is equal to I2. And that's exactly what we wanted to show. So this proves that f is injective. Now we're going to show f is surjective. And we're going to have to move back up to the top, so let me just write some notes up here. The only important notes that we have to keep, I believe, are that this, and this are true. And to show f is surjective, what we're really trying to show here is, for every element j in In plus n set minus In, there exists an element I in In such that f of I is equal to j. So to start, let's give ourselves an arbitrary element j in In plus n set minus In. And our whole goal to prove that f is surjective is to find an element I in In such that f of I is equal to j. And to do that, well, by inspection, if we could send j minus n into the function f, we would get that f of j minus n is equal to j minus n plus n, which is equal to j. So what we're going to do is we're going to show that j minus n is an element of In so that we can send j minus n into the function f and get an output value of j. So let's do that. Now to start, since J is an element of this set, it follows that J is an element of In plus n, and J is not an element of In. Now, since J is an element of In plus n, we know that this means J is a positive integer that is less than or equal to n plus n. However, since J is not an element of In, this means that it is not the case that J is less than or equal to n. So we must instead have that J is greater than n. So putting this together, we have that n is less than J, which is less than or equal to n plus n. And now, subtracting n on all parts of the inequality, we obtain that 0 is less than J minus n, which is less than or equal to n. So notice, J minus n is greater than 0, so J minus n is a positive integer, but we see that J minus n is a positive integer that is less than or equal to n. So J minus n is an element of In. So since J minus n is an element of In, we have that J minus n is an element of the domain of f. So we can take J minus n and send it into the function f, and we obtain that f of J minus n is an element of J minus n plus n, which is equal to J. So as you can see, we have found an element I in In such that f of I is equal to J, namely J minus n. So this proves that f is surjective. So because we've shown f is both injective and surjective, this means we have shown that f is a bijection from In to In plus n set minus In. So there exists a bijection from this set to this set, which we symbolically denote that as this. So this completes step 1 from our plan. Step 2, if you recall, was to show that there's a bijection from this set to B. And we said that we could do that using these first 2 facts. And to see how, well, since there's a bijection from this set to this set, it follows that there's a bijection from this set to this set. That's by our first fact. But by our second fact, since there's a bijection from this set to Im, and there's also a bijection from Im to B, it follows that there's a bijection from this set to B. So this completes step 2 from our plan. The third step was essentially to complete the proof, and we could do so using theorem star. Now, to apply theorem star, we're going to use the fact that there's a bijection from In to A, and there's a bijection from this set to B. And in applying theorem star, we're going to take A, B, C, and D that we have here to be these 4 sets, respectively, in order. And notice, these 2 sets are disjoint, and these 2 sets are disjoint. The reason why these 2 sets are disjoint is because if they were disjoint, then there would be an element in both this set and this set. Well, then that element would be an element of In and also not an element of In, which is a contradiction. So yeah, these 2 sets are disjoint. And we know that A and B are disjoint because that's by assumption. So by theorem star, because we have a bijection from here to here and a bijection from here to here, and in addition, this pair of sets is disjoint and this pair of sets are disjoint, well, we have that there's a bijection from the union of these 2 sets to the union of these 2 sets. But the union of these 2 sets is equal to the set In plus n, which I'll leave up to you guys to justify. So we have that there's a bijection from In plus n to the union of A and B. So what can we do from here? Well, we see that the union of A and B satisfies the requirement to be a finite set, right? There exists a natural number that satisfies this condition, namely n plus m. And n plus m is the unique natural number that satisfies this requirement, and we denote it like this. So really, the number of elements in the union of A and B is equal to n plus m. And from when we started, n is just the number of elements in A, m is just the number of elements in B. And so we have proven that the union of A and B is finite, and the number of elements in the union of A and B is equal to the number of elements in A plus the number of elements in B. So we've proven precisely what we wanted to prove. So this completes the proof. And so yeah, that's pretty much it for this video.